Hello everyone. First of all, I would like to thank you for accepting my communication and thanks for the University of Ouargla for this conference, the first international conference on the chemical matters and environment preservation. Starting with introducing myself, I am khadidja MESSABIH, a PhD student from the University of Science and Technology, Ouargla. My communication is about the isosteric heat of CO2 adsorption on lithium silicates. So, let's start with the introduction. As we all know, nowadays the emission of greenhouse gases into the atmosphere considered as the most threatening problems facing the world. CO2, carbon dioxide, is the major anthropogenic greenhouse gases contributing to global warming and climate change. Fossil fuel systems are among the largest sources of carbon dioxide emissions. Therefore, the capture of CO2 is the first solution and the great challenge facing the scientist community currently to reduce the negative impact on the environment. To mitigate the CO2 discharge from existing industrial resources, various technologies are used. Among them, the carbon capture and storage CCS using a liquid solvent or solid sorbent, especially at high temperatures. From various typical high-temperature adsorbents, lithium silicate has attracted the attention due to the numerous properties such as higher CO2 sorption capacity, fast sorption kinetics, the good cyclic performance. The objective of this work is, first of all, the use of natural sources Algerian diatomite to obtain materials able to capture CO2 at high temperatures. Secondly, the study of isosteric heats on lithium silicate adsorbents. Let's move on methods. In our work, lithium silicate sorbents are obtained by mixing lithium carbonates as lithium precursor to silica, SeO2. This latter comes from two sources. The first, derived from Algerian diatomite, DN, which comes from Algeria. The second, derived from the pure SeO2, which come by Aldrich. The two elaborated materials were named DNLE2CO3 and SeO2Le2CO3, respectively, according to the used source of SeO2. Lithium silicate sorbents are prepared by solid-state reaction at 700 degrees Celsius under atmospheric air. Adsorption isotherms of CO2 are obtained using gravimetric analysis in the range of 400 to 500 degrees Celsius. The isosteric heat at a different coverage rate is obtained from Clausius-Clapeyron equation. So, the reaction between CO2 and our lithium silicate adsorbent follow the following reversible reaction. Coming to our results, and as shown in the two figures, each one presents the amount of carbon dioxide adsorbed at various flow composition from 0 to 100% of CO2 in N2 over the two elaborated materials in the range of 400 degrees Celsius to 500 degrees Celsius. The results show that the amount of CO2 adsorbed over both elaborated materials increases with temperature, indicated the chemical nature and reveals the endothermic nature of interaction between the CO2 molecules and the lithium silicate obtained. Furthermore, for the two elaborated materials, 500 degrees Celsius achieve the highest CO2 adsorption capacity. The following histogram comparing between the two lithium silicate sorbents in the amount of CO2 adsorption capacity at all temperatures. The histogram shows that the lithium silicate material obtained from diatomite highlights a better CO2 adsorption performance with more than 6 millimole per gram than that obtained from pure silica with more than 4 millimole per gram. This result is probably due to the diatomite porosity, which favored the CO2 moving into the lithium silicate framework. The isosteric heat results are determined by the using of the Clausius-Clapeyron equation, which shows differences between our sorbents. Starting with diatomite-based adsorbents, the isosteric energy increases with the CO2 adsorbed amount from 50 kJ per mole to 250 kJ per mole at 4.5 mole of CO2. This evolution reflects the easiness of adsorption initially, occurring over the low-strength sites, followed by chemisorption beyond 3 millimole of CO2. Secondly, for the second lithium silicate based on pure silica, the isosteric energy decreases for 300 kJ per mole as soon as the saturation without coming out of the chemisorption, even at high adsorption content. These results, and especially for the lithium silicate sorbent based with the diatomite, offers a great advantage for the adsorption regeneration because of the low adsorption energy. Conclusion: the adsorption isotherms show that for the two materials, the adsorbed amount of CO2 increases with temperature, which reveals the endothermic nature of interaction between the CO2 molecules and the lithium silicate obtained. The isosteric heat results exhibit complexity of adsorbent-adsorbate interactions and confirm the heterogeneity of the adsorbed size of the two materials. Lithium silicate sorbent derived from diatomite is a potential candidate for CO2 capture. Thank you for your attention.